Hello, I'm Mike McCulloch. Today I'd like to talk to you about Unruh radiation and try to give you some kind of elementary understanding of what it is and where it comes from. But if you look on the internet for a derivation of Unruh radiation, it doesn't really help because the derivations are extremely complex and involve things called Bogoliubov coefficients and transformations, and it's all done in the metric with the machinery of general relativity, and it's extremely complex. But in fact, it doesn't have to be, because you can get the same thing from a much simpler derivation that I'm going to show you, and that I presented in my first book in 2014. So all you do is you start from the uncertainty principle, Heisenberg's uncertainty principle. So the uncertainty in momentum, delta p, times the uncertainty in position, delta x, has to be h bar over 2. So that means if the uncertainty in position decreases, then the uncertainty in momentum increases. So you get more particles buzzing about in a quantum background. You can rewrite the momentum in terms of energy. So energy is P times C, where P is momentum. This is for photons, or which are part of the thermal background that Unruh radiation becomes. So we can change this formula to delta E times delta X is H bar C over 2. And then we know, well, we can assume that the result, the energy we have, is going to be thermal. So we can replace the energy E with Boltzmann's constant K times the temperature. And then we put that in and rearrange it a bit, and we get the T is H bar C over 2 times delta X times K. Now, what is delta X here? Well, every time something accelerates, it sees a Rindler horizon, which appears at a distance delta X of c squared over a away from it, in the opposite direction to its acceleration. So we can say that delta X is c squared over a. So if we put that in, we get T is H bar A over 2ck. And this, barring a missing factor of pi, is the Unruh temperature that was derived incredibly in a very complex way by various people, Fulling, Davis and Unruh, back in the 70s, based on the area of Hawking radiation, which is very similar. So this is very similar to the Unruh radiation formula, the standard one. As I said, just pi is missing. But the derivation is much nicer, because it starts to explain what Unruh radiation actually is. So Unruh radiation is simply the momentum uncertainty released when the position uncertainty is reduced by a horizon. So you could talk about things like squeezed space. When you squeeze space with a horizon, momentum appears within it, and this can be interpreted as a thermal background, hot particles moving about, full of momentum. The other way to do it, and I discussed this in a previous video on the informational derivation of QI, is that what happens when a horizon appears, when something accelerates and a horizon appears behind it, this horizon, from the point of view of the particle, is destroying information about the cosmos, and that reduces the entropy, and that can't be allowed. So a lot of heat has to appear to ensure that the entropy of the entire universe goes up. And this is the Unruh radiation. You can derive it this way as well, and I did it in a previous video. Okay, so I hope you like this simpler derivation of Unruh radiation. Despite what you find online, it's not something to be feared. Bogoliubov transformations are not needed. You can derive it in this very simple way, and it helps us to understand exactly what it is. It's a marriage of quantum mechanics and relativity. Okay, so I hope you've enjoyed this short, and I look forward to speaking to you next time. Goodbye.